Good morning. I am Dr. István Szintai. Let me show you the world in my eyes. In this episode, I will use your ability to imagine because the side view of a sphere is a circle, so your exercise will be to imagine the sphere in my work. As we get back to the clean paper, we can imagine a sphere that not rotates regard to the irradiation and irradiated from infinite distance, so the irradiation is parallel. In this case, the sphere would have an infinite night side and an infinite day side, and the terminator line is the line between them. The night side is declared to be the non-radiating side, so the temperature will be 0 on the surface because we are talking about a sphere that non-produces energy in their inner body. And the day side will have some temperature. The subsolar point is the closest point to the irradiation, where the incoming radiation incident angle is 0, or if we think that we are on the surface, then the irradiation is directly above our head. In this model, every surface point has a constant temperature because only the incident angle will matter. This is called the standard temperature model in the scientific literature. And the isotherm points are located as a circle on the surface, but we see it from side view. So the scattered line represents the isotherm points. So this is a circle, but this is a side view of the sphere. Okay, but how does the temperature disperse on the surface? Before we jump into the abstract world of mathematics, at first I would like to change the thinking because we will not count how much will be the temperature on the surface with a certain irradiation. The surface will have a certain temperature, and we will count what is the performance that keeping balance with the temperature radiation. We can pick up a line from the subsolar point to the terminator, and we can choose a unity from this line, one unity from the subsolar point and one unity at any gamma incident angle. And as you can see on the plot, the incoming irradiation changes by the function of cosine. So we can write up these two equations. From these two equations, we can count that the temperature disperses along the surface as the fourth root of the cosine function of the incident angle. I wrote you up two more expressions that I will use later. Okay, but we can find a scientific article that tells us that on Moon, the temperature disperses as the rule we counted. So very well. Let's move on. There's another model. It's called the fast rotating model in the scientific literature. You can imagine a sphere that rotates so fast that temperature difference cannot be measured between day and night. And the rotational axis is perpendicular to the radiation. And again, this is irradiated from infinite distance, so the radiation is parallel. In this situation, every surface point has a constant temperature as well as the standard temperature model. And the isotherm points are located as a circle on the surface again, but we see it from side view, so the scattered line is a line, not a circle. And the subsolar point, it's not going to be a point in this model, but it's going to be a line along the equator. Okay, but how does the temperature disperses along the surface? To figure this out, I will import a mathematical rule. The common surface of a slice of a sphere and a sphere, and the common surface of a spherical cup and a sphere, is written down with the same rule, and this surface is proportional to the width of the slice. So if we slice the sphere with equal width slices, then the surface area will be equal as well. Again, if we put a snooker ball into an X slicer and we execute in mind the slicing, then there will be the same amount of colored dye on each slice, having the same width. So we will slice the fast rotating model, but only the northern part, let's say north and south, because fast rotating model is a symmetric model, so it's okay if we count only the one side. We will slice the northern part of the sphere with equal width slices. And if we make infinite number of slices, then every slice will be isotherm. We will make infinite number of slices, but the rule I show you only in 3 slices. First of all, we can define an incident angle to each slice, as you can see on the plot. After that, we can write up the performance balance equation for each slice. For that, we have to count each surface areas. The radiative surface area is a bit easier because the rule was to slice the sphere with equal surface areas slices. So the rule is very simple because 4 pi times radius on square is the surface area of a sphere. So half of a sphere is 2 pi times radius on the square. Radius will not matter because radius and square will be on both sides of this equation. So with the radius, I don't count. The irradiation is the front view of the sphere. So this is a circle, territory of a circle we have to count. So it's a two-dimensional thing. To count the territory of X3, at first we have to count a sector of a circle, which is a radius on square times pi, multiplied by a ratio between alpha and the whole circle. If we count in radians, then it is 2 pi. And from that territory of sector, we have to subtract a triangle, which we can count easily because 2 sides and the sinus of one side divided by 2 is the territory of a triangle. So with the alpha angle, we can count both of it. And if we want to count the territory of x2, at first we have to count x2 plus x3 and then subtract x3. So for general form, we have to count 2 sectors and 2 triangles, and we have to subtract them from each other. If the angle functions works in radians, then it would be look like this. With this expression, we can count the temperature. And in this function, the only variable is the irradiation. So to visualize this function, we have to choose one irradiation. I choose the average total solar irradiance at 1 astronomical unit. With this value, these temperatures looks. As the first slice is the closest one to the subsolar line, so this is going to be the subsolar temperature. If we increase the number of slices, then the subsolar temperature will be equal with this expression. Knowing the subsolar temperature and knowing the angle, we can verify whether the temperature dispersing rule is it the same as the standard temperature model or not. So we can write up the subsolar temperature and the cosine, the fourth root of cosine, the incident angle. And as you see, we cannot, and as you see, these two functions give the same numbers. So if we make 100 slice, then the computer will be not able to show both of them because the difference is so little between the two functions. If we increase the number of the slices, then the difference will be less. between the two functions. It is out of the scope, the mathematical proving that the two functions is the same when n goes to infinity. And as we can say that the temperature dispersing rule is the same, and there is another expression between the irradiation and the subsolar temperature. We can make a summarization with the constant surface temperature models. One is the standard temperature model, the other one is the fast rotating model. And as you can see, the temperature dispersing rule is the same, and the connection between the irradiation and the subsolar temperature is almost the same, only a dimensionless number is the difference. If we think that there is a line between the subsolar point and a pole, then it could be the noon line. Then the standard temperature model and the fast rotating model is the two extremes. And on that noon line, we can find these temperatures, as you see on the plot. There is one more constant surface temperature model when we think that the sphere rotates in a chaotic way, but with infinite speed, so every surface point has the same temperature. This is called the isotherm model. If you can imagine that any other rotation situations must be in between these models, where the one extreme is the standard temperature model when the sphere not moves, and the isotherm model is the other extreme where the whole surface is isotherm. And I cannot imagine other situations that is out of these models. So this number between the subsolar temperature and the irradiation must be between 1 and 4. If we enter the performances we counted in the second episode, you can see that at the 90% of the surface, there is that 4 degrees of change because of the irradiation. So we have that 4 Celsius we are looking for in the first episode, but not the direction, because from these equations, the subsolar temperature should be higher close to the sun and lower far from the sun. But we have that 4 degree. It's very interesting. And in addition, if you scroll back in this video to the plot of Dr. Larson, you can see that the temperatures on Moon is almost underneath the standard temperature model. And from general knowledge, we know that when the sun is directly above our head, then it's surely above 20 or 25 degrees, where the fast rotating model would give. We have two celestial bodies that seems to fit to be in between these two models. Do you think that rotation should be a first-line parameter in the performance balance equation? If you say yes, then I infected you. Before we pop champagne, rotation is not a parameter in the performance balance equation as science thinks. In the simple thermal model, you can see the equation from the article that counts the temperatures of asteroids. We have discussed the blue letters. On the left, there is the available incoming performance from the sun. On the most right, there is the Stefan Boltzmann law multiplied by 1, so the science can think that the standard temperature model valid at any time. And we have 3 dimensionless numbers with white color. On the left, A is albedo. This is the fraction of the incoming performance that is reflected back as shortwave radiation. On the most right, epsilon, is the emissivity that maybe some surface property takes a role in temperature radiation. A and epsilon can be between 0 and 1. And there is one more, the beaming effect, the beaming parameter, eta, that can be between 0.6 until 3.5, but this is not a closed scientific debate. And Beaming parameter is not interpreted in the case of Earth and Moon. And I quote from this article, eta is not a physical property of an asteroid, as it can vary due to changing observing and illumination geometry, aspect angle, heliocentric distance of the body, phase angle, and wavelength of the observation. Quotation closed. So none of these dimensionless numbers are related to rotation. Why rotation is not a parameter in the performance balance equation? I don't know. For me, it seems logic to have a parameter dedicated only to the rotation. So the next episode, I will leave the main road of science and I will introduce rotational index into my train of thought. Be well, and don't forget the sun will rise tomorrow morning for sure.